Good morning, sir.
Good morning, Namrata. Namrata, invite your friends to join.
Okay, sir.
Okay, so welcome back, students. Am I audible to you all?
Yes, sir.
Okay, so hope slides are also visible to you.
Yes, sir.
Okay, so we discussed about different types of the vectors, and among that, the most important one we talked about the plasmid and the viruses, and among the viruses, it's the bacteriophages, and what are their properties, how their property we can utilize for our vector. So then, in previous lecture, we talked about some of our vector that was plasmid based and how we developed them and what are the property these virus vectors are going to have and how we reach to the what vector we are going to have. And among that, we talked about the first vector developed by Bolivar and Rodriguez, and on whose name it's also given PBR322. And what property it is going to have, how the name of this vector came, and uh, that become a practice and future also whenever you are naming that vector, we are going to name that in a similar fashion. So then we are talking about what the useful property of this PBR2 is going to have, and the genetic and physical map of the PBR2 is available with you. And when the map is available, it simply means a complete sequence of the vector is going to be available for you, and by which you can design whatever you want to, whatever action you want to perform. And the most important feature that we are seeing of this PBR2 and is important also because many of the exam, because generally this is a general vector and all of a basic understanding of the vector that we are going to have, all is based upon this vector. So among this important feature, first thing is size. So its size is going to be 4363 base pair, simply 4.3 kb or kilo base pair, we can say it, and which make it so small. And as we mentioned previously, the virus should be less than 10 kilo base pair. So if we keep, if we add additional 6 kilo base pair over it, so then its size is going to be around 10 kilo base pair. So that is bit around a range that we can transfer to our cells also. So that's why its size is small. So we can load around 6 kilo base pair over it when we construct a recombinant DNA molecule. So that's why it is a manageable size and we can use it. So this is a good property of this vector. And another, we are moving to further what are its usefulness. This is a size one, we mentioned it. Second usefulness is about the marker that we mentioned. We can screen it because we can recognize it. And this marker that we are going to use it in this case, that it carries two antibiotic resistance genes. So this is, you must note that whenever we are writing the feature of this vector, so first thing refer to its size, then coming to the protein level markers it is going to have, and the two genes to resistant gene is going to have, that is going to be the ampicillin, this is an antibiotic, and second is going to be tetracycline. So these two antibiotic resistant genes are going to be there. So if you grow any cell which is harboring this plasmid, this vector is going to have these genes in them also, and these genes are going to code for a gene that is going to help you in digesting this ampicillin or the tetracycline. So the one enzyme that called the beta lactamase. So the some lactam group is there in some this antibiotic that these genes code for those enzymes. If the enzyme is present within the cell, then that cell have ability to degrade these antibiotics. So this is the one that's the important property that is there in this vector, that it have a PBR that have ampicillin and tetracycline resistant gene in them. And one more thing is that that we're talking about the cloning site. It must have multiple cloning site. Yes, this is a feature is there. It have multiple cloning site, and in the multiple cloning site, an important feature is also there that this multiple cloning site is also present within your genes also, like ampicillin, tetracycline genes. These these resting sites are going to be there. So what happen if the restriction sites are there? It means if you cut with the restriction and then when you put insert at this restriction site, what the insertion is going to lead? The insertion lead to the inactivation of any of these two enzymes, depending on at which site you inserted your insert. So insertion new DNA integrator that has been restricted with PSP1, PVU1 and SCA1. So these three restriction sites are present in the gene that is there that code for the ampicillin gene, ampicillin resistant gene. So if you are cloning, if you are loading your insert, any of these three sites, they are going to inactivate your ampicillin resistant gene. So what is going to happen in this way? So in the earlier case, when both the sites are going to be intact, both the genes are going to be intact, the cell harboring the vector going to survive in both of these antibiotics. But if a case is there, now if you grow the cells which are inserted, which have the insert, they are not going to grow in in the ampicillin gene. So if you are cloning at the ampicillin. And if you talk about the second one, that is the tetracycline resistance that have the BAMH1 and HIND3. So if you want to clone at the BAMH1 site and the HIND3 site, that is going to inactivate the tetracycline. So depending upon what gene you want to inactivate, you can choose your restriction enzyme to open it up, and then you can insert your gene that you want to insert using the ligase enzyme. So this is the way, the property that we are going to do, the selection that we are going to do. This is called the insertional inactivation. Means if the insertion is going to be there, then only genes are going to be inactivated. If no insertion is there, then the no inactivation is going to be. So if the cells are surviving both of your antibiotic, it means there is no cloning happen, no insertion is going to be there. So you can use any of several kind of sticky ends. So sticky end that you feel, whether of the BAMH1, PSCA1, PVSP, PST, PVU, and HIND3. So any one of these sticky ends you can utilize for cloning at these sites. So further, if we move to let's see what it's going to have. It's designed another property that's it have origin of replication in it. So this is origin of replication site. This you need. This is a map of this vector. So in the map of this vector, as we mentioned, that it has the two ampicillin resistant gene and the tetracycline gene. And with that, you need origin of replication. If there is no origin of replication, it's not going to sustain itself within the cell. So it has the origin of replication. Then the second one, it has the HIND3, BAMH1, and SAL1. These restriction sites are present where? These are present in the tetracycline resistance. TET is a tetracycline resistance. So this is green color is a gene that is for the tetracycline resistance. And then if you see the next one, that is going to be your thing that we have here is second one is a PST, PBU, SCA. So these are present where? These are present with the next gene that we call the ampicillin resistant gene. So two genes resistant gene are there. One is the ampicillin resistance, second is the tetracycline resistance, and third is going to be your origin of replication. So these are the properties that are going to be there within your one. Origin of replication can sustain. Its size is small, 4.3.4363 base pairs. Then the two resistance genes are there, tetracycline and ampicillin, and around 1, 2, 3, 4, 5, 6, 7, 8. 8 restriction sites are there. So means multiple cloning sites are there depending on your restriction enzyme that you are cutting with the depending on the sticky end your insert is going to have. You can use the corresponding restriction enzyme to get a sticky end in your vectors, and you can use ligase to clone your genes. So further coming to the more property, as we talk about a property of your plasmids, the copy numbers. So it have a relatively high copy numbers. So how many numbers are there in a cell? So in a cell, around 15 copy of PBR322 can exist. So that is also an important property. And this copy number is not just limited to the 15, it may go high also to the 100,000 to 3,000 by plasmid amplification in presence of a protein synthesis inhibitor such as chloramphenicol. Means if you are growing if you inserted your vector inside the cell and you treat your cells with the chloramphenicol, what these chloramphenicol are going to do? These chloramphenicol are going to inhibit the protein synthesis. So once the protein synthesis is going to be inhibited, that is a trigger for the replication. So this replication is going to be multiple fold, means that we are saying in the normal condition, copy number is 15, but if you treat with the chloramphenicol, the copy number is going to rise to 1000 to the 3000. Okay, so this is going to lead to a good yield of the recombinant PBR322. So this is a good high copy number, and copy number may can go through the 1000 to 3000s. Now this is the properties of the vector that you are going to have. But now the case is, now the important point, that is how we generate. So how the Bolivar and Rodriguez generated this vector. So as we are saying, the first laboratory practice also we mentioned that the construction of your vector means what property your vector is going to have. We have to construct them. What property you need, we need to construct it. We need to bring our desirable properties. So the plasmid in fact designed in such a way that the final constructed just these desirable properties. What are the? It must have origin of replication, selectable markers, multiple cloning sites, and smaller size, and multiple copy number. So all these properties are going to be there. So for what, from where you got these? So PBR32 comprised DNA derived from 3 different naturally occurring plasmids. So whatever the property we are referring here, these all are there from the 3 different plasmids. So from 3 different plasmids, we took our desired property and we joined into a single plasmid. So this is the one that found. So from where we got it? So when we are talking about properties, property means we are talking about ampicillin resistance, tetracycline resistance, origin of replication, and it's means you need to remove other things also. We need promoters also so that these enzymes can express. Okay, so ampicillin resistant gene that originally reside in plasmid R1. So this is a plasmid R1. So here the thing, you should get a thing between, you need to differentiate between whether it is a designed vector or a naturally occurring plasmid. Naturally occurring plasmids are named on the basis of strain which are harboring them. So here the plasmid R1. So R1 is going to the strain of your cell, like if it is E. coli R1 strain harboring this plasmid. Okay, so that is also this is a plasmid typically antibiotic that occur naturally population of E. coli R1 strain. Okay, so we took a plasmid from the R1. So this R1 is going to give you gene from the ampicillin resistance. So what you are going to do, we are going to restrict, digest, and isolate the gene which is going to code for the ampicillin resistance. Second is the tetracycline resistance. This gene is being derived from another plasmid. Its name is R65. It is a second antibiotic resistant plasmid, so it is also naturally occurring in the equilibrium. So this is a naturally occurring plasmid. So now to the third part of your gene of your vector, that is the origin of replication. So origin of replication of PBR32 is derived from direct manipulation of vector in host cell is originated from the PMB1. So PMB1 is another plasmid which carry the your origin of replication. So from these plasmid we got this one, and this PMB1 is that you got from the col E1. So col E1 is again another plasmid. So from that you get the colicin producing. Okay, colicin is an antibiotic which is present on the on plasmid. Okay, so from these 3 plasmid you got 3 different regions of your plasmid, and that you join them using the ligase, and that yield you the vector that you are going to have. Okay, so the first thing R1. So R1 gives you ampicillin resistance. second is the R65, it gives you tetracycline resistance, and third is the PMB1. What it give you? It give you the origin of replication. So what you did, then you again you are having col E1. So this origin of replication, tetracycline, all of these you transfer to the col E1 plasmid. So first you did, you combine the col E1 and R1. So with it particularly you get from the R1 you transferred the tetracycline ampicillin resistant gene to the col E1, and you name this as a PSF2124. Now this is also again not a successful plasmid one, and you further recircularized fragment. So now this you short it down, you cut unnecessary regions in it, and with that you incorporate the eco-R1 restriction sites. So eco-R1 restriction sites are there at the both the end, and you recircularize it. Then what you did, then from the PMB1, you take out the origin of replication. Again, you do the same proper process. You cut it down and recircularize it. So this gives you the origin of replication. Now you combine what? You combine two, PSC101 and PMB8. So now what is going to get? A new plasmid is going to have origin of replication, and it is also going to have PS or tetracycline resistance. So now you are going to have two things. Now this is PMB9. In the PMB9, you are going to have a origin of replication, you are going to have tetracycline resistance gene. Now, this PSF2124 and PMB9, you mix it and you merge it. So the same the digestion and the joining. Now, when you treat it, you lead to a new vector that is the origin of replication, ampicillin resistance, and the tetracycline resistance. This vector is called PBR322. So this is a bit larger in size. So again, you need to cut it short. So we again rearrangement, cutting down and shifting from one direction to another direction. Means if you see here, ampicillin is on the left side, tetracycline on the right side, you reshuffle it, so the plasmid further becomes shorter, and this shorter one is called the PBR313. Then again, it's not did your job, still a bit larger one. So what you did is again two fragments, break it down and remove certain more fragments, so that your plasmid further becomes smaller in size. This new vector called the PBR322, and this is the first successful vector which served the job that we all want to have. So this is how the plasmid vector being constructed, starting from the natural occurring plasmid to the your vector plasmid. So here the difference between the natural occurring plasmid, they can't serve you as a vector, and but these PBR32 it can serve you as a vector. It can carry your gene, it can replicate, it can help you in the finding whether the it will lead to the formation of recombinant or not. So it is going to be the thing. So what it have the confusion from the R1. It have from here it got this tetracycline we got from the R65, and origin of replication we got from the PMB1. So these are the things that you are there on your PBR32, and in this way you got. And so first successful vector is how Bolivar and Rodriguez will construct this vector. So simple thing that if you wish to construct a vector in your life, so what you need to know is the property, you need to know the sequencing. So what property you want to use, the similar sequence you pick up and redesign it, so ligate, digest, and ligate it. That is construction of your vector. Okay, so now the next type of the vector is PUC8, also called the PUC8. So what it is going to have, it is a vector that has a property of Lec selection plasmid. So previously we mentioned we use a method in which we use antibiotic as a selection method, but now here we are not using antibiotics. We are using both another one antibiotic also. We use one more selection. So what is PUC8? P is the stand for plasmid. U and C stand for University of California. So this PUC8, 8 is a number. So this plasmid University of California 8. So it is a descendant of PBR322. So means what are the things are there in PBR322? Some of we further modified this PBR322 to get this new vector, or we import some more things. That means it is going to have whatever things are there in the PBR322. Application of origin and ampicillin resistant gene. So what if we keep in this enzyme, this vector? So in this vector, we keep only. Is it everything is visible to you? Am I audible also?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, so simply it's not hanged at my end, so just wait for me. Okay, now it's first fine. Okay, so what it is going to have? It is going to have origin of replication, that was the integrated to same thing, and second thing it is going to have emphasis gene. So two of these components. So if you see previous slide, so what this component has emphasis and the origin of replication. This component we keep it, and this tetracycline resistant component we removed. So after removal of that, what you are having, that we calling this is the original one. So the nucleotide sequence of it has been changed so that it no longer contains unique restriction sites. So further you shorten it down, you cut it down so that what change it get, the restriction site that was present within the emphasis resistance, you remove. So the thing that we are saying, we are now not cloning, uh, we are not insertion inactivating the gene. So selection that we are going to do is going to be a different way. So what we remove the tetracycline. So on the base of tetracycline, you can't select. And second thing, also you remove the resin site from the your sequence. So that you can use for the selection uh, this gene. So but what you are doing here, all of these genes are now clustered into a short segment of LAC-Z gene. So what you did? Now you inserted one more gene here. So what gene you inserted? That insert is called short segment of LAC-Z gene. So hold the gene that if you know that the lack of RON, I think you have studied in your first or second year. In the lack of RON, that code for the 4 genes, that 3 genes, Z, Y, and E, I think that among that one gene is chosen, that is a Z. It is called the LEC-G gene or LEC-Z gene. In my time it was Z, in your time it is going to be G. LEC-G gene carried by the pocket. And now restriction sites that we are wrapping, this restriction site, all the restriction sites got clustered in this LEC-Z gene. So that insertional inactivation that we are referring, now we are not insertionally inactivating your antibiotic resistant gene. But what we are inactivating, when we are inactivating this lecture gene. So what this lecture gene do? This lecture gene is going to go, it is going to code for the gene that is going to use, that you can use for the metabolism of your lactose. So this gene that we are going to use it. So Pocket has 3 important advantages that led to becoming one of the most popular E. coli cloning vectors. So this is the vector. As we mentioned that your PBR322 is not a no more vector of a choice because advanced vector are there that we are choosing for further cloning. So among them, Pocket is a further advancement. One of the advancement that is going to be, it have a lag selection one. So the first is this phosphorus and the manipulation involves the concept of it accompanied by chance mutation within the origin of replication. So first thing is the one mutation occur in the origin of replication, and this mutation is chance mutation. You yourself can modify this origin of replication, but when you're developing this vector, while you're using your strategy, a mutation occur within the origin of replication, but it leads to this mutation. Generally occur this mutation due to the inactivation, but here in this case, this mutation due to the overactivation, and this overactivation increases the copy number. So in previous vector, PBR2, we found that the copy number is coming to be 15, and if you want to increase to 1,000, then you need to treat with the clone and equal. But here in the normal condition, this copy number, this vector have a copy number of 500 to 700. even before amplification, is even without the treatment of the clone anicole. If you treat that with a clone anicole, then definitely its number is going to be match the what number you are talking about. So PBR 322. So this is the first important thing that this plasmid packet, that is also called the Lec selection plasmid, have is having significantly high yield of your vector even without the treatment of the clone anicole. So the compared to, if you are comparing with the PBR322, its copy number is 10-fold, 20-fold high, 50-fold high as compared to your PBR322. And the second advantage is that recombinant cell can be achieved by single step process. So here you need not to go for a multi-step process. In previous case, what was there? What is the thing? We were selecting multiple times. So what we are doing? So first, we are saying that this is a vector, and these are the two genes. This is a T, and this is going to be A, ampicillin. So we are saying if cloning is there, then ampicillin is going to be inactivated. So in this case, what we can do, we can, if we are cloning in the tetracycline, so in the cloning in the tetracycline, then those cells which are surviving, we can't tell that these all the cells are recombinant or not. Okay, so once we clone them, then we go for a replica plating. So whatever cells are surviving on the tetracycline, then we have to plate them on the ampicillin. So those which are dying on the ampicillin, they are going to be your recombinant one. So here you have multiple steps. So step 1, step 2. So this is going to be one better thing, that it is a step 1 monostep process. So here itself, uh, on a plate which is going to have ampicillin resistance, you can screen whatever the cells which are appearing here, you can tell that they are recombinant or not. The recombinant selection is going to be based on the X-gal. The okay, X-gal, if you just directly keep the X-gal in the media, and X-gal is a substrate for your beta lactamase, sorry, no, your LEC-Z gene, so which is going to help you in the detection of that. So the second advantage is that identification of a cell can be achieved by single process by plating onto agar medium containing ampicillin plus X-gal. In this case, we can't do that, because if you add both the antibiotic, then all cells will die, because cells is now, or those which got transformed, they are sensitive to the second antibiotic, which leads to the insertional inactivation. But in this case, the X-gal is not a negative selection; it is a positive selection. So negative selection means whatever is not surviving is going to be your recombinant. What are surviving, that are not your recombinant. So it's called the negative selection. So here we are going for the positive selection. So with both PBR322 and PBR327, selection recombinant of two-step procedure requiring replica plating from one antibiotic medium to the another antibiotic medium, a cloning experiment with packet can therefore be carried out in half a time. So just in once you transform, and following what appears, by seeing the transform, you can tell that whether they are recombinant or not. So you can see the map. So what is going to be there? So this is a LEC-Z. This one more important feature is the size. So you can see that size of this is going to be 2.735. So when the size is 2.375, you compare with your 4368, I think this was the size. So it is half the size, if you simply can say. So if you just simply half it, then it's going to be 2188. So it is not half, but more than half, but still, if you subtract it, so it is going to have 8, 1, and 13, 6, and 1. So this much size smaller than, so this is this much extra load your vector can carry. So this is another property of this packet. So what this packet is going to have, we mentioned that LEC-Z gene is going to have your multiple cloning sites. So what are clustered here? You have HIM3, you have PST1, SAL, ACC1, HIM2, BAMH1, SAMA1, ZAMA1, and ECOR1. So restriction sites are there. So another vector in this line is the PUC line is going to be PUC18. So it's further going to have more restriction sites in 3, and additionally you can see that KPN1, SCA1, and these are the additional sites you are going to have in it. So in this way, you can simply say that PUC is going to be a bit better than your PBR322. How it is going to be better? One, in size wise, size is very small, copy number is high, selection is going to be better. So let's lead to be an improvised vector. So now if you say that from where this LecZ gene is going to be there, you came. So as we're talking about pedigree, so pedigree wise, whatever the pedigree of your PBR322 was there, so what you did, take the PBR322, cut down the your tetracycline one and insert LecZ gene. That insert LecZ gene you can get from the you can get from natural cells, because these LecZ gene is in the genome of your E. coli. So from the genome of your E. coli, take out this Lec gene component. So now the third advantage is that lies within the clustering restriction sites. So this is the one which allow DNA fragment. So DNA fragment, two different sticky ends are there, EcoR1 at one end and BAMH1 at the other end. So the different ends are there, you can clone without resorting to the additional manipulation such as a linker attachment. So all this you can do. So multiple cloning sites are there, sticky ends are there, you can generate them and you can insert. So BAMH1 EcoR1 are there. Packet vectors carry different combination of restriction sites and provide even greater flexibility and type of DNA fragment that can be cloned. So this again, so whatever this more number of restriction sites are there means more options are there with you. So you can generate a respective sticky ends and you can clone within these vectors. So furthermore, restriction site cluster, these vectors are same as a cluster equivalent to the M13P series vectors. So this is how you are generating it, and so DNA clone into number of PUC series can be therefore transferred directly into the M19 and P counterpart. So if you want to just digest it, you can remove your site and you can transfer this site to the selected gene site that I mentioned. Therefore, you remove the exchange to the new vector also. Okay, so GCMB314 in vitro transcription clone vector. So this is another vector so what is there? It is a vector that's having a role in the transcription. So now what we are going to do, we are going to talk about something like transcription of clone DNA. So when we are saying the transcription thing means we are going to talk about bit of the expression. So what it is going to have this vector PGEN3Z. So it is a very similar to PUC vectors, means it is going to carry amplitude resistance and also going to carry Lec genes. So later continue a cluster of extreme site among exactly the same. In distinction is that has two additional short pieces of DNA. So what is additionally going to have? Each of the recruitment site attachment of RNA polymerase enzyme. So it is called the promoter sequences. The promoter sequences are there which play a role in the binding of RNA polymerase. So if RNA polymerase is going to bind there, that leads to a transcription. So if the RNA polymerase won't bind there, then there is going to be no transcription. So this is a vector that we call the expression vector. So now this vector is going to be an expression vector type. So what is now going to have? So in case of PUC, we mentioned that I have antigen resistance, Lec genes, origin of replication, and it have a promoter, the T7 promoter and SP6 promoter. So at both the ends, different promoters are there. So depending on what direction you are going to have, you can use the T7 promoter and the SP6 promoter for your expression. So these two promoter sequences are there. These two promoter sequences are going to play role in the recognition and going to lead to the transcription of your gene. So one gene got transcribed, then translation machinery is there to translate your mRNA. Okay, so I think Okay, so for the few more points, we can talk about this GEM3. So two promoter sequence lie either side of the cluster of the RNA site leads to introduction of new DNA. Depending on which direction you want to insert, you can go for. This means a molecule is mixed up with purified RNA polymerase in the test tube. Transcription occur and the RNA copies of clone fragment are synthesized. The RNA is produced could be used for the hybridization probe or might be required for the experiment in studying the RNA processes. So this is the thing that is going to occur in it. It's going to have another feature that you insert, that means can go for the transcription. So depending on what polymerase you are going to use, if you are going to use GCMB314 polymerase, then the transcription is going to be in that direction, and if you are using the second one, then the direction of your reverse. Okay, so further more information, more thing about your PGEM3Z. The promoter carries the PGEM3Z and other vectors in these types are not standard sequence recognized by the E. coli RNA polymerase. So this thing you need to check that these are not recognized by the RNA polymerase, so means they are not going to work always. So instead, the promoter is specific to the RNA polymerase by T7 bacteriophages. So these are the RNA polymerase T7. So means in normal cells, if you transform these vector, then they are not going to transcribe. So then what you need? Then you need to insert in your host itself. You need to manipulate so that they can synthesize the RNA polymerase that can recognize that promotes. Other than the RNA polymerase SP6 phase, these RNA polymerase are synthesized during the infection of the E. coli with one or more phases that are responsible for transcribing genes. So both are the phase originating one. So now you need to modify your vector host also so that they can express the gene that you need to. Okay, so now I think then it is going to be overload if I am going to talk about much more. So I'm stopping now. Further property of this PGEM3Z I will talk in next class. Uh, then in next class we will finish the vectors that are base that you need. So it's a long list are there. So few more vectors we'll talk about that based on the M13 pass and your normal bacterial pass. So two more vectors are going to be there other than these, and then we'll conclude. Okay. So now we are end of this session. So before ending the session, I would like to request you anything that you feel that what we have talked today is not you are not able to get that, you are not able to assimilate that. So please tell me. Any query that you didn't get, or you need a further bit more explanation at any point.
Sir, when you will be sharing the slides?
Slides of this module or the previous module? You ask me slide for this module or previous module? I will do tomorrow. I will share the slides tomorrow because today I have lots of classes. So time is today's schedule is a bit packed. Tomorrow is a bit free, so I will share slides tomorrow by morning. Okay. Okay, Yukta?
Okay, sir.
Okay, so I'm giving you 5 minutes to just rethink what we have talked about and then come up with the questions, and then we move for the attendance. नमस्कार डॉक्टर साहब, क्लास चल रही है। So welcome back, students. Hope so you come with come up with any question. If no query, then we should proceed for concluding it. So please turn on your camera while I call your name. Adish. Adish.
Present, sir.
Atoiba.
Present, sir.
Present, sir.
Ayushi.
Present, sir.
Demetrius.
Present, sir.
Devanshi. Devanshi. Ishita.
Present, sir.
Janvi.
Present, sir.
Kshitij.
Present, sir.
Manaswini.
Present, sir.
Namrita.
Present, sir.
Nandini.
Present, sir.
Nehal.
Present, sir.
Rupal.
Present, sir.
Rupal.
Present, sir.
Saiba.
Present, sir.
Sanjana.
Present, sir.
Shakti.
Present, sir.
Shivani.
Present, sir.
Tanvi.
Present, sir.
Tridev.
Present, sir.
Vivek.
Present, sir.
Vanshika.
Present, sir.
Yukta.
Present, sir.
Yuvraj. Okay, so thank you, students. So all are present. Stay safe, stay happy. Good day.
Thank you, sir.